Hi YouTube, today I'm going to show you how you can simulate spread of COVID-19 using your handy HP RPN calculator. Now to do this, I'm using the existing SEIR model and I'll be factoring in the effect of social distancing, which we're doing now by staying at home, as I am now. This SEIR model stands for susceptible, exposed, infected, and recovered. And the way I'm going to model this is by taking a set of differential equations for the change in susceptible, exposed, and so on over time, and then watching how those populations change at different time points. I'll be doing this using the semi-implicit Euler method, where I essentially take the previous values for these populations and then add in the rate of change, ds over dt times the change in time parameter dt. There are 10 inputs which I've put into my RPN program. The starting susceptible, starting exposed, infected, and recovered. The alpha parameter, which is 1 over the incubation period for the virus, novel coronavirus, nCoV in this case. Beta, the contact rate. Gamma, 1 over the mean infectious period, and then rho for social distancing. And you can see how these are factored in here. For the susceptible population is lost at a rate of negative beta times the susceptible population times the infected population. Exposed is beta times susceptible times infected. It's added to exposed minus alpha times exposed. So that's where the virus has incubated and now can spread. And then infectious is alpha times the exposed population minus gamma times infected. That's now past the infectious period and become recovered. And then for change in recovered, it's gamma times the infected population. I've set the variables a through j to these parameters that you see here. And I have all this code listed under the label C on my calculator to run the simulation. Now, before I run the program, I'll show you the parameters I'm using. For alpha, it's 1 over the incubation period, which a recent paper lists as 5 days, so alpha will be 0.2. Beta, I only was able to get knowing gamma and the R0 value. So first I'll look at gamma. So the infectious period is known to be 2 days. 1 over 2 is 0.5, so gamma is 0.5. R0 for this virus is known to be 3.5. So if I, for example, had COVID-19, on average I'd pass it to 3.5 people. So we know gamma and we need to know beta. Gamma was 0.5 here. If I multiply 0.5 times 3.5, voila, 1.75 for beta. Now for the initial values, I'll use 9,999 out of a population of 10,000 being susceptible. Start with 1 person exposed. I have to use these as proportions in my equations, and then the set infected and recovered is both 0. I'll set the dt value for the simulation as 0.1 days and the maximum number of days, the end time point, as 40 days. Okay. So now I'll go ahead and turn on my calculator and run the program. I'll type in execute and then C and enter. A, what do I want to set A to be? So let's go back here. A is susceptible, so I'll put 0.9999 RS. Now B, I want to set as 1 in 10,000. Okay. Oh, RS. C as 0. These are leftovers from the last simulation. D is 0. Now E is 0.2, that's alpha. F is 1.75, that's beta. Gamma is 0.5. And for social distancing, I'll start with 1, which is no social distancing. For rho, that's some proportion of the contact rate. So in a second simulation, I'll set that at 0.8 or 80%. But for now, I'll have no social distancing. For I, the dt, that's 0.1. And the file parameter, 40 days for Tmax. And I'll let that sit and run. And I'll get back to the video once it is done running. Okay, finally my program's finished running, so let's see those values of S, E, I, and R. First I'll recall A, and then C, the proportion that are susceptible. 2.387 E negative 1. So 2.387 times 10 to the negative first, or about 24% remains susceptible. Now I'll take a look at B. 25% roughly exposed. Okay. About 10% infected. And one more. 41% recovered. So quite a bit of the population has been exposed to the virus and either ended up infected or finally recovered. Some 10% of the population is infected. And just imagine what a consequence that would have for hospitals in this imaginary city we're talking about. Now let's see what happens when we simulate this again with social distancing. I'll press execute and C, enter. I'll go back through and put in my initial conditions, 0.9999 RS, 0.0001 RS, 0, 0, 0.2, 1.75, 0.5, and now let's try 0.8. So 80% of the contact, that's normal because, I don't know, 20% of the population staying home where there's just 20% less interaction between people. People are staying 6 feet away from each other, some proportions paying attention, and let's see what happens at 40 days to that proportion exposed and infected particularly. So I'll go ahead and press enter. Oops, RS I mean. I is good, J is good, and let that run, and when this is finally done, I'll come back and we can compare the results at 40 days with social distancing added. Let's see what happens to that time point for exposed and infected, and think about the consequences of that. Okay, it's been a few more minutes, and now I have the results from the simulation with social distancing with that parameter of 0.8 for rho. Okay, now I'm going to go back and recall susceptible. 74%. Recall exposed. 11%. Let's see infected now. Oh my gosh, 3.6% for that. And recovered. About 10%. So you can see in this case there's quite a large proportion of the population that's still susceptible, and just 11.5% exposed and 3.6% that are infected. With just 80% of the contact in the previous simulation, we end up with 3.6% infected as opposed to a little over 10% infected. A huge downward movement of that peak number of affected cases. And you can imagine in this simulated city or in real life, that would be important for reducing the burn on hospitals. With so many cases in a hospital, they'd run out of equipment, PPE, ventilators, goes under equipment, and drugs, and there would be a higher mortality rate. And this is why flattening the curve through social distancing is so important. And I want to tell everyone, please stay at home right now. Please stay 6 feet from other people to keep COVID from spreading. And with that, thanks for watching. And if you'd like to run this simulation yourself, the link to my text file with this code in RPN is listed in the description of the video. Once again, thank you for watching. Bye now.